So it's a totally relatable scenario for pretty much anyone listening to this deep dive right now. You sit down, you ask an AI a question, maybe it's about, I don't know, a niche piece of code or some historical event, and it gives you this highly confident, beautifully structured, and completely wrong answer.
Oh, absolutely. It's the classic hallucination problem.
Right, and it leaves you staring at the screen just wondering, you know, how can these models be so unbelievably smart at predicting the next word, but so utterly terrible at knowing when they are, well, actually unsure about something?
Yeah, I mean, it really highlights this fundamental paradox in modern artificial intelligence. We have these massive systems that can pass the bar exam or architect complex software,
Hmm.
but they lack the most basic cognitive function of self-doubt.
They just don't doubt themselves at all.
Exactly. To put it bluntly, they do not know what they do not know. And they will hallucinate a completely fake Python library with the exact same, the same linguistic conviction as they would use to tell you the capital of France.
Wow, yeah. So today, we're doing a deep dive into a really fascinating new position paper. This is by Papamartu and a large research team published in May 2026, and it completely flips how we think about solving this exact problem.
It really does. It's a major shift in perspective.
Yeah, the paper argues that we need to build what they call Bayes consistent orchestration for agentic AI. And the core premise here is just a massive paradigm shift. Instead of trying to force the AI's brain, like the LLM itself, to understand its own uncertainty, we actually need to build a separate, purely mathematical manager to supervise it.
Which is a crucial pivot for the entire industry. I mean, for
Yeah.
years, the default strategy has just been trying to make the LLM the ultimate decision maker.
Greg, it's the boss of everything.
Right, we've treated the language model as this monolithic intelligence. But this paper argues that prediction, which is what the LLM does in decision making, have to be completely decoupled. We need to treat the LLM as just a component, a text generator inside a much larger structured mathematical system.
The way I'm visualizing this, and tell me if this makes sense, it's like dealing with the brilliant but incredibly overconfident junior employee.
Oh, that's a great analogy.
Right. Like this intern has memorized the entire company database. They always have an answer ready, and they will confidently tell you, yes, the Q3 budget was approved, when they actually just misread a spam email.
Exactly, yeah.
And traditionally, developers have been trying to send this employee to years of expensive management training, or trying to literally alter their brain to teach them risk management. But the paper says, well, that's a dead end. Instead, just hire a seasoned manager, an orchestrator, to sit above them, take their output, and mathematically weigh it against costs and risks.
Yeah, and setting those stakes is so important because where AI is heading right now changes the math entirely. If you're just chatting with an AI to brainstorm blog post titles, the stakes are virtually zero.
Right. Who cares if it messes up a title?
Exactly. Simple prompting heuristics like asking the model to think step by step using chain of thought, that works fine. But we are rapidly moving into high-stakes, real-world agentic behavior.
Oh, for sure. Real money, real systems.
Right. We're talking about AI agents authorized to spend a marketing budget, modify live production code, or even diagnose critical server outages in real time.
Yeah.
You just cannot rely on prompting tricks when an overconfident hallucination could take down an entire company's infrastructure.
No, absolutely not.
That's where rigorous Bayesian decision theory becomes the only viable safeguard.
Okay, so before we get into how this Bayesian manager actually operates, I really think we should explore why fixing the model's brain directly is considered a dead end. Because historically, teaching the neural network to gauge its own uncertainty, that was the holy grail, wasn't it?
It was, for a very long time, the entire field of Bayesian deep learning was dedicated to this exact problem. The ambition was to train neural networks to maintain what they called a posterior over parameters.
A posterior over parameters. Okay, break that down for me a bit.
Yeah, sure. So in a standard neural network, a connection between two nodes has a fixed weight. It's just a single number.
Okay.
But the Bayesian approach argued that instead of a fixed number, every connection should maintain a probability distribution, like a bell curve of possible weights.
Oh, I see.
Yeah, and this would theoretically give the model a built-in mathematical sense of its own internal uncertainty at every single layer.
But wait, modern LLMs have hundreds of billions of parameters.
Yeah.
Trying to calculate a probability distribution for all of those sounds, I mean, computationally impossible.
It is effectively impossible. The dimensional space is just way too massive to map that probability surface accurately. So researchers tried approximations.
Like what? What did they try?
Well, the most popular method was deep ensembles. The idea is pretty straightforward. You just initialize 5 or 10 different versions of the model with different random seeds. You train them all and then run them simultaneously.
Okay, so like a committee.
Exactly. If they all give the same answer, the system is certain. If they wildly disagree, the system knows it's uncertain.
I mean, running 5 massive LLMs for every single query just to figure out if it's lying to me sounds like a fantastic way to bankrupt a startup on AWS bills.
Oh, the computational cost is astronomical. But, and this is a key point for the paper, what they point out is that even if you had infinite compute, the ensemble approach fundamentally breaks down at modern scales anyway.
Wait, really? It just stops working?
Yeah. We run into phenomena like the cold posterior effect and something called epistemic uncertainty collapse.
Okay, I definitely want to dig into the mechanics of that because epistemic uncertainty collapse sounds incredibly ominous. What exactly is collapsing inside the network?
It all comes down to over-parameterization. Modern LLMs have so many parameters, billions of these adjustable dials, that the network is incredibly flexible.
Right.
When you train multiple versions of a model on the same data, you'd hope they learn slightly different functional representations of the world. That diversity is what gives an ensemble its power to measure uncertainty.
Because they make different mistakes.
Exactly.
Yeah.
But recent research, and the paper specifically cites work by Kirsch from 2025, shows that in these massive models, that functional diversity simply collapses. The models are so large that they all just settle into the exact same wide, flat basin of mathematical solutions.
So they don't even disagree anymore.
Right. If you run an ensemble of 5 massive LLMs, they don't give you a diverse set of opinions. They essentially become a monolith, and they all make the exact same confident mistakes.
Wow. But hold on, I have to challenge this premise just based on how we interact with these models daily.
Yeah.
If I look at the API output of an LLM, it's literally spitting out probability scores for the next token, right? So if I ask it, what color is the sky, and it generates the word blue with a calculated internal probability of 99.9%, isn't that literally the model telling us exactly how certain it is about a fact?
That is probably the most pervasive misconception in generative AI right now.
Really?
Yeah. And the paper tackles it by drawing a hard line between 2 things: syntactic uncertainty and semantic uncertainty.
Syntactic versus semantic. Okay, walk me through the mechanism there. What's the difference?
So think about what the model is actually predicting. It's predicting the next piece of a word. Syntactic uncertainty is about the grammar, the exact phrasing.
Okay.
The model might be genuinely unsure whether the next word should be appears or looks or is. That reflects uncertainty about syntax. Semantic uncertainty, on the other hand, is about the underlying truth or meaning of the statement.
Oh, I think I see where this is going.
Yeah, an LLM can generate a completely fabricated historical event, a pure hallucination, and assign a razor-sharp 99.9% probability to every single token, because the grammar of the hallucinated sentence flows perfectly.
Oh, wow. So the token probability is really just measuring how confident it is in its typing skills, not how confident it is in the facts.
Exactly. It's highly confident that the word blue is grammatically the best word to follow the sky is, but it has zero fundamental understanding of whether the sky is actually blue in the real world. A high token probability absolutely does not equal task-level truth.
That is wild.
Yeah, the LLM is fundamentally a black box text generator.
Yeah.
It just cannot reliably self-report its epistemic uncertainty.
Which means we really just have to abandon the dream of the self-aware Bayesian brain. We just accept the LLM for what it is, this incredibly powerful but completely unself-aware pattern matcher.
Right.
And that brings us to the core solution of the paper, which is this Bayesian control layer, the orchestrator.
Exactly. If we accept the LLM as just a predictor generating text, we need an entirely separate entity to be the decision maker interacting with the real world.
Okay, let's elevate that workplace analogy we used earlier into something a bit more structured. Reading this, it felt very much like a courtroom to me.
A courtroom. Okay, I like that.
The orchestrator is the judge sitting on the bench. And the language models, the coding agents, the retrieval tools, they're all just witnesses taking the stand.
That framework works perfectly for understanding the math, actually, because the judge doesn't care about the internal psychology of the witness. The judge isn't trying to model the firing of synapses in the witness's brain.
Which would be like tracking the LLM's billions of parameters.
Right, which we know is impossible.
Right. The judge only cares about the testimony itself. They take the evidence presented by the witness and use it to update their own internal probability regarding one specific question, like, is the defendant guilty or innocent?
Yes. And in Bayesian decision theory, That guilty or innocent question is called a latent variable.
Latent variable, okay.
The orchestrator maintains what is known as a belief state over this specific low-dimensional latent variable. So instead of tracking the entire universe of the LLM, the orchestrator just tracks one core unknown.
Like, will this generated code pass the unit tests?
Yeah.
Or what's the root cause of this memory leak?
Exactly. And the mechanism for updating that belief state is just pure Bayes' rule.
Hmm.
As the LLM agents generate text and submit their evidence, the orchestrator shifts its probabilities.
But what I find fascinating is how it decides when to stop gathering evidence and actually take an action, because it relies on calculating the expected value of information.
Right, which is where this moves from theory into practical economics.
Hmm.
Let's say the orchestrator is currently 85% certain that a piece of code contains a security vulnerability.
Okay.
It could call an expensive, slow static analysis tool to get more evidence, but it mathematically weighs the potential gain in certainty, the expected value of that new information, against the literal cost of querying the tool.
Factoring in API fees, latency, all that.
Exactly. If the cost outweighs the value of moving from 85% to 90% certainty, the orchestrator just stops querying and rejects the code.
It's constantly doing this calculus, balancing the mathematical utility against real-world constraints. And the paper actually proves this isn't just academic theory, right? They outline several concrete design patterns.
Yes, three main scenarios.
Let's look at their first scenario, code generation, because I think we can really see how this mathematical tempering works in practice.
Sure. In the code generation scenario, that latent variable we discussed, let's call it dollars, is binary. Will the generated code compile and pass the tests? Yes or no?
Simple enough.
Right. And you have various agents involved. One LLM writes the code, another acts as a reviewer, maybe a third acts as a security scanner.
But the orchestrator doesn't just average their opinions together because, well, not all agents are created equal.
Exactly.
The paper introduces a reliability weight, denoted as alpha, to temper the likelihood of the evidence. So, if the code-writing agent has a historical track record of hallucinating completely fake API endpoints, like 30% of the time, the orchestrator assigns it a low alpha weight.
Correct.
So when that agent says, this code is perfect, the orchestrator essentially takes that testimony, mathematically raises it to a fractional power, and flattens its impact on the overall belief state.
Meanwhile, if the static security scanner has a 99% historical accuracy rate, its alpha weight is extremely high. The orchestrator dynamically adapts its trust based on measurable performance. It aggressively scales the input mathematically before it ever updates the probability of the code passing.
Okay, a binary pass-fail is relatively straightforward, but what happens when the orchestrator doesn't have a simple yes or no choice? Like, what if it's managing a massive menu of things going wrong all at once?
That leads to the second scenario.
Right, the second scenario dives into multi-agent deliberation during a production server failure, complete chaos, alerts going off everywhere.
Here, the latent variable is no longer binary. It's a discrete hypothesis space, which the paper refers to as $dollars. The orchestrator maintains a probability distribution across a wide menu of potential root causes.
So is it a database lock, a misconfigured load balancer, or an upstream API change?
Exactly. So the system spins up specialized diagnostic agents. A log-reading agent starts parsing the server logs. A separate code review agent looks at the last 5 commits. They're essentially debating the cause in real time, generating high-dimensional text.
And as they generate that text, the orchestrator maps those observations into probability updates for each hypothesis in $dollars. It just watches the probability distribution shift. And crucially, it has predefined confidence thresholds. So if the probability that the failure is a database lock hits, say, 95%, the orchestrator abruptly cuts off the LLMs.
Right. It stops the debate. It prevents them from burning more compute in an endless conversation loop, and it alerts a human engineer with the highly probable diagnosis.
It applies a rigid mathematical braking system to the traditionally messy, rambling nature of LLMs, which transitions perfectly into their third scenario.
Cross-task routing.
Yes, which is all about resource management from the very first step. The system has to decide which agent to even wake up. The paper discusses learning a cross-task competence parameter psi.
This directly targets those compute costs we mentioned earlier. Imagine an enterprise system that has access to GPT-4, which is incredibly smart but expensive, and then a much smaller, highly fine-tuned local model that costs pennies to run.
Okay.
When a new data processing request arrives, the orchestrator must decide who gets the job.
The text highlights the use of Thompson sampling for this routing, and I wanted to ask you about this because, based on how I'm reading it, Thompson sampling allows the system to balance exploration against exploitation.
Yes, exactly.
So it maintains a beta distribution over the success rate of the cheaper tool. Exploitation means it uses the expensive proven tool when it absolutely needs high certainty.
Right.
But exploration means occasionally it deliberately routes a task to the cheaper tool just to gather data on whether it can handle that specific type of query. Is that right?
Yeah, that is a highly accurate summary of the multi-armed bandit math happening under the hood, yeah. By utilizing Thompson sampling, the orchestrator samples from its current belief about the cheaper tool's competence. If the sample is high enough, it takes a calculated risk and uses the cheaper tool.
Wow.
And as it observes the outcome, it updates the posterior distribution. Over time, it learns exactly which subtasks the cheap model can handle flawlessly.
So it naturally routes work away from the expensive model whenever mathematically viable.
Exactly. It turns AI orchestration into a continuous cost optimization engine without sacrificing the quality of the final output.
Knowing that this math is actively driving down API costs makes this incredibly appealing, but it raises a massive architectural question.
How do you build it?
Yeah. If I am an enterprise engineer, how do I actually build a system that's constantly doing Bayesian updating without completely choking my infrastructure? The paper outlines 7 desirable properties for practical design, and a few of them really address this integration challenge.
Right. The first major principle is treating utilities and costs as dynamic mathematical variables rather than static rules.
So instead of trying to write a system prompt that says, never share user data, which we know an LLM might easily forget or be tricked into ignoring.
Which happens all the time.
Exactly. Instead of that, the orchestrator handles it. It assigns a massive mathematical penalty to privacy breaches within its utility function. Even if the LLM strongly suggests calling an external API with sensitive data, the orchestrator's math evaluates the expected value of that API call, subtracts the massive privacy risk penalty, realizes the expected utility is deeply negative, and blocks the action.
The risk is abstracted entirely away from the language model.
And to address your question about choking the infrastructure, we really have to look at the property of belief state distillation. This is the mechanism that allows the system to actually scale.
Yeah, explain that one. Because when you have multiple agents debating and iterating over dozens of steps, the interaction history becomes enormous.
Right. In a traditional setup, you have to feed that entire massive transcript back into the LLM's context window for every new step, which is incredibly slow and eats up millions of input tokens.
Exactly. But with belief state distillation, the orchestrator doesn't need the transcript. It compresses that entire sprawling history of text into what statisticians call a sufficient statistic.
A sufficient statistic.
Yeah, it extracts the probabilistic essence of the conversation, the updated mathematical belief state, and discards the raw text. So the LLM only needs to be prompted with the current focused state of the task, not the entire history of how it got there.
Okay, compressing the history makes total sense, but let me press on this latency issue a bit more. Even if we compress the text, we are still introducing an entire new layer of management into the software stack.
Sure.
If we are constantly calculating expected utility, doing multi-armed bandit math for routing, and updating posterior distributions using Bayes' rule, doesn't this Bayesian manager inevitably become a massive computational bottleneck?
It's a totally valid concern, but I think it misunderstands the weight of the math involved. The paper specifically targets low overhead as a core property.
Okay, how so?
The math the orchestrator is doing is happening in a very low-dimensional space. It's tracking a handful of variables like the binary pass-fail of Delaus or the discrete hypotheses in dollars. It's performing basic calculus and probability updates on small matrices.
Right.
Compared to the computational heavy lifting of running a forward pass on a 70 billion parameter neural network to generate text, the Bayesian updating takes literal microseconds.
Oh, wow. So the math is trivial compared to the text generation.
The math is nearly invisible from a latency perspective, and in practice, it massively reduces overall system latency.
Because it stops them from talking endlessly.
Exactly. By preventing redundant tool calls, aggressively cutting off agent debates the millisecond the confidence threshold is reached, and routing tasks to faster, cheaper models via Thompson sampling, the orchestrator is saving orders of magnitude more time than it actually consumes.
Okay, that makes it highly practical. And the paper also emphasizes that this needs to be accessible, right? Like Engineers shouldn't need a PhD in statistics to implement this.
Exactly.
The complex Bayesian updates happen entirely under the hood. As a developer, you're just exposing simple dials in your interface. You set a confidence threshold variable to 95%, or you adjust a cost penalty slider to aggressively prefer cheaper tools. And the orchestrator handles all the calculus of hitting those targets.
It beautifully bridges the gap between rigorous academic theory and usable industry middleware. But of course, the authors are realists. They dedicate a significant portion of the paper, particularly in the appendices, to the reality checks.
Because the real world is messy.
Exactly. This system, while elegant, has specific vulnerabilities.
Right, garbage in, garbage mathematically optimized out. The biggest vulnerability they highlight seems to be the observation models. The orchestrator relies entirely on mapping the high-dimensional nuanced text output of an LLM to a clean, hard probability score.
Yes.
If that mapping formula is flawed or misspecified, the orchestrator is perfectly executing flawless math on fundamentally bad data.
And that misspecification leads directly into the most dangerous trap in modern AI, the problem of correlated evidence.
Oh, this is such a relatable issue. If you ask 5 different instances of an LLM the exact same question, they might all give you the exact same wildly incorrect answer.
Very common.
And the reason is they share the same massive pre-training data, they share the same underlying transformer architecture, and they might even be responding to similar system prompts.
Right. And if the Bayesian orchestrator is naive, it will look at those 5 identical answers and treat them as 5 independent pieces of evidence.
Oh, that's bad.
Its mathematical confidence will artificially skyrocket. It will calculate that it has a rock-solid consensus, when in reality it just has a single, deeply ingrained bias repeated 5 times.
It's the exact same dynamic as human echo chambers. If you ask 5 people for their expert advice on a topic, but they all secretly just read the exact same Wikipedia article right before talking to you.
You don't have 5 independent experts.
Exactly. You don't have a consensus. You just have one Wikipedia editor's opinion echoing in a chamber. The orchestrator has to be sophisticated enough to recognize the echo.
Which requires the system to utilize what the paper calls dependence-aware evidence pooling.
Dependence-aware evidence pooling.
Yes, the mathematical updates have to group highly correlated sources. The orchestrator must be explicitly programmed to treat those 5 similar LLM outputs not as independent trials, but effectively as a single joint observation. It limits the impact they can have on the belief state.
That's brilliant.
Furthermore, it requires aggressive recalibration from real-world outcomes. When the system makes a confident decision that turns out to be wrong, it must severely penalize the alpha reliability weights of the agents that contributed to that echo chamber.
Tempering their influence on all future decisions.
Exactly.
It has to mathematically map out the echo chambers and actively discount them. It's a really robust safeguard. Well, as we wrap up this deep dive, I want to crystallize the core takeaway for everyone listening. The next massive leap in agentic AI systems that can actually operate safely in enterprise environments, manage budgets, and fix code, it's not going to come from building a massive LLM that simply knows everything. We are not going to achieve reliability by trying to train an AI intern to never make a mistake.
Reliability comes from structure. Whether you're building a simple coding assistant today or architecting a massive enterprise workflow tomorrow, you have to identify exactly where the uncertainty lives in your system.
Cleanly separate the text generation from the decision-making.
Yes. Stop asking the language model if it's sure about its answer. It does not know. Build a Bayesian orchestrator that independently calculates whether the model's output is reliable enough to act upon and knows exactly when to stop and alert a human.
Which leaves me with one final, slightly provocative thought for you to consider. We've spent this entire time marveling at the concept of the perfect mathematical manager. An orchestrator that ruthlessly, flawlessly weighs the expected value of human input against the latency and cost of pausing the system to get it.
Right.
But if we actually succeed in building this, if we create a Bayesian system optimized purely for operational efficiency, will there inevitably come a day when that orchestrator runs the multi-armed bandit math and calculates that asking a human for clarification is simply too slow, too expensive, and mathematically suboptimal?
That's a chilling thought.
By striving to make AI the perfect manager, do we risk engineering a system that permanently manages us right out of the loop? It is definitely something to keep in the back of your mind the next time you authorize an agent to take control.